Hochhauser. I'm CyberSecurity Alliances Manager for NVidia. And I'm here today to talk to you about RAG for bags. I will explain what it is in a second. So the first thing I wanted to say, usually we have an agenda. I was going for the anti-agenda. So what we're not going to talk about today is AI ops, mostly because about 3 years ago, I was here on this very stage speaking about AI ops. But if we think about the intersection between AI and DevOps or IT, then there are two sides to it. There is a side of the IT operations where it's AI ops, as an example, sits. And this is where we think of AI systems and the way we want them to be self-monitoring and the best way possible to be managed on their own. And then there is the space of the IT service management, which we're going to touch upon today. And this is things like auto ticket resolution and root cause analysis and all of these things that are meant to help us operate better in regards to these incidents and not the systems on their own. So this is few examples of things that we internally as NVIDIA thought of in order to implement as part of our bug system. So again, things like ticket summarization or auto routing for tickets, so auto resolvement. And I'm sure each one of these is something that you would also find interesting to implement. And I guess the very first question would be, why not to use just ChatGPT or any of the foundation LLMs to solve these problems? So when we talk about any enterprise-specific applications, and now talking about IT or DevOps problems is just one side of it. But when we think of even any type of chatbot for HR or for cybersecurity, for retail, for virtual assistant for meetings, all of these things require custom LLMs. The foundation LLMs are the brains that are behind generative AI, but they're not ideal for enterprise use cases for a few reasons. So first of all, they're frozen in time, right? So they were trained up to a specific point in time. And if we think of organizational data that is ever changing and flowing, it's not good enough. The other thing is oftentimes they would hallucinate or would just make up something and would not necessarily also give you the source of where they are grounding their answer. And when we think of our use cases, if you're gonna send a ticket somewhere to be solved, or you wanna show a specific document that is about how do we resolve the incidents, then we'll have to reference something that is actually exist as part of our knowledge base. And the third thing is that obviously we're talking about things that are domain specific. So our organization has a different set of needs according to whatever the domain you're operating in, the industry, but also again different methodologies. And this is why in these use cases we often use RAG, Retrieval-Augmented Generation. In raise of hands, if any of you have heard about this term before, know what it is. Okay, so definitely some people. So the thing about RAG that is different between just approaching an LLM like GPT or Mistral or Gemini and asking it a question, that you would take the question and before you would send it off to the LLM, we'll first go into a retrieval process. Now, the retrieval process, which includes embedding, we'll go over it later, takes that question and is going and performing a lookup in a knowledge base. The knowledge base is per organization, and then when it retrieves it, it sends to the LLM the original question, but also the document where the answer is supposed to be found, right? The specific, I will say, context. And then the LLM acts as basically a generator. So if you think about it, we are treating the LLM as a tool that knows how to phrase answers. So it's very good at native language processing. So it will know how to frame the answer very well according to the question, but also we give it the specific reference to where the answer is going to be. This way we keep it fresh, right? So we go to the knowledge base, and if something updated or changed in the knowledge base, then we'll get it. And also we are making sure that the answer is grounded, and as I said before, we don't have any issues with that. So this is an example of RAG that we built internally for bugs. I will play it and then we'll talk about it a little bit. So if you can see here, this is our NVbug system, our internal system for bugs. I'm writing here a query in native language, right? It's the way I would do it. So I'm asking it to show me, to please show me bugs that are missing a config file, right? This is the reason the bug is. I chose something super simple, so I won't be exposing anything confidential. And then it's able to retrieve for us. It goes to a knowledge base, right? The data warehouse where all the bugs are stored, and retrieves for us the bugs that are relevant. You can also see that there are different questions, prompts almost, that I can ask it. So what is the main problem in a specific bug and how it can be reproduced? Who is assigned to a specific bug, or even a list of bugs which are assigned to me. And again, I think we also see here the huge power of, we tend to dismiss or disregard the power of having this native language interface, but oftentimes this is a difference between people ending up using this chatbot or this feature or not. Now, what we are going to talk through today is a new feature we just released again internally for our use, which is called Find Similar Bugs. So if you would think of this, it makes perfect sense why this would be a feature very useful, I'm sure, to every single person sitting here in the room. So because that would allow us to minimize bug management if there are duplicate bugs, and we all know that oftentimes when we're looking through bugs, we see that plenty of them are addressing the same issues. So if one is closed, the others should be closed as well. And we want to be able to just reduce, right, the volume and assist with triage. So if we think of like how the world is based when it comes to bugs, I said before it's about finding similar bugs, but we have the duplicate bugs, so bugs which are exactly alike, right? Then we have another set of bugs that we'll say see also. These are bugs that you would want to look through when you're trying to resolve your own bug and get some ideas for it. And when we're saying similar bugs in terms of text similarity, some of these would end up being duplicate bugs, right? They belong to that part. And some of them would end up being see also bugs, so bugs where you can get an idea of how to solve yours. And then some of them wouldn't be relevant at all. So if you remember, I showed you before this RAG architecture. But if we think of, I'm sorry, it's like blinding everyone. I'll move forward. The knowledge base down there, in this case, is the data warehouse of the bugs, right? So we have a Gremlin data warehouse of bugs that has 182 something bugs. And we are also able to create two different data sets, hand tagged, like human tagged. One of duplicate bugs of 9,000 bugs, and then see also bugs, 35,000 of these. Now, the other thing on my anti-agenda for today is that we're not going to actually focus on an LLM. I know, surprising, shocking, but we're going to focus on the retriever part. And retrievers are essentially the piece that is responsible to finding the most relevant, as we said, either document or text from the database. So in order to retrieve the right and relevant document or piece of data, what it does, it encodes both your question, so the prompt or what you entered it, and both the database. We'll go over what encodes, what is the embedding essentially is, and then it retrieves for you the most relevant or the most similar answer, which is what we are trying to achieve, right? We are trying to find the most similar bugs. So this one is much better, I guess, architecture. First, because it's not white and it seems like it's not blinding everyone, but also because I lied before, right? So I wasn't showing what the actual retrieval process included, but it includes embedding model, which I will go over in a bit, but we are gonna embed in case so a user gives a prompt, it can go directly to the LLM, or this prompt, this question is going through embedding, and after it's embedded and turned into a vector, we'll search for it alongside other embeddings and find the ones which are the closest. So because I promised I will talk about embeddings, and I'm sorry again if anyone is blinded, but embeddings are vectors. So they're capturing the semantic meaning of the words, and it's our way, just think of turning meaning into the space dimension. So essentially, we want to make sure that words that are close from a semantic perspective, so they mean around the same things, they have similar meaning, would be close to each other on the vector. So we will be representing data as like points on the vector space, and we're able to say that the spatial proximity, so how close they are on the vector, is an indication of how similar they are. So if you see here, we would expect like sort of men and women to be far from each other on their vector, the same dimension or the same distance that would be between queen and a king. And then we see that a cat and a kitten would be very close to each other, and then a dog would be closer to a cat than a something like a house. And again, this is our way we can create many different type of embeddings depending on what is the similarity that we are looking for. But here we are going to do the same for our bugs. So we'll take the indexing data set. So we have, as we said, we have a huge data set of bugs, 182 of them, 1,000 of them. There are all of these columns, right? So we have like the model, the origin, the graphic origin, division, etc. And we create embeddings for each one of them. So we'll be placing, just think of it, we'll be placing each one of these bugs on a vector that is by each column, so how far they are from each other when in regards of the description, how far they are from each other in regards of the origin, etc. So they will be clustered, as you can imagine, according to that. So basically, we are taking the bugs textual info, so the way they are from the data warehouse, and we are indexing them, as I said, by using embedding into Elasticsearch. It acts here as sort of a vector database, if you heard the term. So this is actually what it is. And Haystack is an open source framework developed by DeepSet that is allow us to perform hybrid search. So we'll have here both lexical and semantic search, which again, I'll cover in a little bit. So when a query comes in, so when we'll have a new bug coming in, we want to find similar bugs, right? This is our purpose. We want to give a certain, we have all of these details about a specific bug, and we want to be able to retrieve all the similar bugs. So the retriever itself, and again, as I said, this is like a hybrid search. It would perform both lexical search. Here, the BM25 is a model by Elasticsearch, and E5 is a model by Microsoft, which is semantic search. Lexical search is just very straightforward, is when you are looking for the actual term, right? So if there is sherry in a whiskey cask, you would look for each of these words specifically. I'm going back. But if we're talking about semantic search, you would actually look for the meaning of the words. So what it will do, it will take this new bug, will do embedding for it, right, for this new one, and then it will search for other bugs which are around the same area in different vectors. So this is the way it's going to retrieve it. So now we're going to go through the research questions. So basically how we are able to develop it through time and see if we need to do fine-tuning or not. And I think that would be just relevant for any of you thinking of doing something like this, and what is the thought process. So the first thing we actually wanted to check is whether bugs on their own have like duplicate bugs and related bugs, the C also bugs. Do they share higher text similarity than other bugs? So we essentially took, as we said, we had also a set of duplicate bugs. So we took these sets of duplicate bugs and we compared them to a set of random bugs, and we were trying to see if they were closer to each other on the vector, right? If they were similar, more similar to each other. And we found out actually that it was not. So again, this is sort of, you can see in blue the duplicate bugs versus the random bugs, and here you can see the C also bugs versus the random bugs, and you can tell that they're not necessarily similar, like similarity is not higher with the duplicate or C also than the random ones. The second thing that we wanted to check though, that if we can use bug similarity, so if we can still change somehow the embedding in order to do that. So we did a couple of things. The first one was we took 3 columns together, so the synopsis, the description, and the bug type fields. We created one field, so one column out of these 3 that we felt like were the most significant when we were trying to find a similar bug, and we generated embeddings from this one. Now, when we took, again, we took the duplicate bug pairs that we know that there is the original bug and we know what is its duplicate, and we tried to do embedding for it. And then we tried to see if we can calculate the top X most similar bugs using face, and if one of them ended up being the duplicate. So before, just I will go and explain what is face. So I'm sure I'm now again reminding everyone of their days, I don't know, studying computer science or math or bad things. But essentially, if you think of this, we don't, when you think of a vector that has 182,000 data points, you don't want to search for all the neighbors that are close, right? You want to be able to search for I will say a limited set of these. And there are many ways to do this when we're looking for this is the nearest neighbors problem, right? The ANN problem. But oftentimes we'll just take a subset and we'll say, okay, this is like the cluster which is closer, or do something like this. What Face does, and this is by Facebook when they were still named Facebook, now Meta, this is the F stands for, and AI semantic search. What it does is basically it has an approximate, so it is able to have like an approximate amount of neighbors, and if we compare it to the actual amount of neighbors, so after that we search for the real amount of neighbors that we have, then we are able to calculate what is the recall, right? The recall would be the number of neighbors that it showed us, so the numbers of bugs, similar bugs that is found versus the actual number of similar bugs. So going back here, what we did is we took the duplicate bug set. I'm sorry if I'm blocking you from seeing, maybe I'll go that way. It took the duplicate bug set and the C also bug set, and we did an evaluation using recall metrics. So again, when we're putting in through any new bug and we're looking for anything similar, now we'll be doing this with a new embedding that we just posted. And with that embedding, we'll calculate for this new column what is the similar bugs. We'll end up having, let's say, 4 similar bugs, and we'll look whether they match the C also bugs that we were expecting to see. We went over this. Again, this is the way it's going to look. We'll find top 3 or top K most similar bugs, which are the neighbors. So in this case, we are able to see the results got a little bit better, but they're still not that good. So recall 3 is when we get the top 3 result, recall 5, top 5 results. And the number essentially tells us how many of these were, in fact, duplicate bugs. So if we think of this this way, so 35% of the related bugs we are able to find if we retrieved, we got 10 answers, the top 10 answers, and out of the top 10 answers, the similar bugs, we're able to find the duplicate bug like 35% of the times, which is nice, but obviously still not good enough. So our next approach was to fine-tune the embedding model. So up to now, we did use an embedding model, which is really strong and powerful, the E5, but we didn't fine-tune it, meaning it wasn't necessarily better at putting on the vector bugs versus classifying, right, different animal types, so, or any of these other things. So we ended up training, and what we did is basically giving it the examples of the things that do work, right? So we are fine-tuning it and giving it sort of examples. This is how I would classify. I would take this bug, and this is a similar bugs, the C also bugs, I would match to it. And we feed that into the model, which is really important, not in inferencing. So we are not running it as we did before, just tell us what are the results. We are fine-tuning it. So we are retraining it with the data that we know is correct, which will obviously make it better. It always does, but this is a process that requires a lot of compute power and hassle. So we try to avoid it in the first place. So this made a difference of almost 50% improvement. We can see in like the different recalls. Still not good enough though. And the last thing that we wanted to do in this case was re-ranking. So the way re-ranking works is it's on top of the embedding. So we said again, we take the bugs, we place them on the vector. They're wherever they are, and that's great. But oftentimes, this will create other problems with semantic proximity, because you can think of, let's say, different answers that would still be very close, but they're not right in our context. So as an example, I remember I've read this question about where was the last World Cup? And if someone would post an answer, where in the world, another similar question, where is the world my cup of coffee? Then that would be very similar to it from a textual, right, from a semantic similarity perspective, but that wouldn't necessarily be at all close in terms of what we're looking for. So re-ranking is just adding another layer and saying that all of these responses that we get answered, after that, we weigh in another model. And this model we teach before was different types of good example and then bad example. So we'll punish it whenever it's like finding, we'll send it like non-duplicate bugs as an example, and these would be ranked very low. And we'll send it duplicate bugs as an example, and these would be ranked very high. And in that sense, we'll teach it sort of, re-ranking would be taking these top 10 results we just said that would come off the embedding model, and then re-rank them. So we'll rearrange them according to this model that we have taught and we have like shared good and bad examples with. This is a way, again, that it works. You'll put a query, you'll first use the embedding, and then on the embedding, we'll be re-ranking the questions once again. Now I'm going to show you how it worked. This is like the second feature, so how the find similar bugs worked. So I chose one of the first bugs from the last one. And here you see the NVBugs Copilot up there. There is a summary. Also, the summarization is a classic ML problem that we solved. And then the similar bugs, you see it was thinking, was able to find bugs that it felt were similar. We have here the similarity score, 90% or could be 36%. It's still in beta, so still we can give thumbs up and thumbs down in case something is not working as we expected. And again, I just think this is sort of an example showing you, we are talking about bugs, but any of the logs or any of the things you're going through, which are textual, are things that we can use LLMs or embedding models, either out of the box, going through a process and trying to fine tune or re-rank or make it better. Some of these things are available as open source and you can check it out yourself. This is a LinkedIn to my this is a QR code to my LinkedIn profile. It was a pleasure. Thank you.